Hello, welcome to the Astrocheminar. After a short summer break, we are back with our fall series of Astrocheminars. First, we have a few announcements. Please feel free to submit abstracts through our website by sending us an email to any one of us really for contributed talks. Our dissertation award application window will probably open in the new year, but if you have graduated in the last 2 years, you are eligible. So please, we encourage you to start preparing now for applying. Remember that all these Astrocheminars are up on YouTube. So just search for Astrocheminar and you'll find them. Please subscribe to the channel so that we get a custom URL. We're pretty close to 100 subscribers now. Today we have two great talks. First up will be Olivia Harper Wilkins. Olivia Harper Wilkins is a PhD candidate at the California Institute of Technology, where she works on observational astrochemistry. Olivia graduated from Dickinson College with a BS in chemistry and mathematics, after which she spent a year as a Fulbright research fellow with the Cologne Laboratory of Astrophysics Group in Germany. At Caltech, she has been supported by an NSF Graduate Research Fellowship, an NRAO Student Observing Support Award, and an ARCS Foundation Scholarship. She's also an artist, and she recently wrote and illustrated the ebook Astrochemistry for the American Chemical Society's In Focus series. Today, Olivia is going to talk about using molecules to map physical parameters in Orion Kl at high spatial resolution. Olivia, you can take over now.
Great. Thank you so much for that introduction and for having me. I'm excited to share some of the work that I've been doing as part of my PhD thesis work. But before I get into that, I just want to give a shameless plug for the Astrochemistry book, because I'm really proud of it. And I'm really proud to have written it and also illustrated it. So you can find it on the ACS website, in your institution's library, or on Google Play. I also want to say that I'm able to submit like minor revisions a couple times a year. So if you notice any typos, because they're inevitably still in there, please let me know and I'd be happy to update it. But since this is the Astrocheminar series, hopefully we all know and appreciate that interstellar molecules are useful tools. They're useful tools in a variety of ways. We can use them as chemical clocks to understand stellar evolution, both to understand what's going on as a star is evolving, but also to figure out at what stage it is in its evolution. We can use molecules in the interstellar medium as probes of physical conditions, and we can also use them as representatives of extreme chemistry. So chemistry at extremely low pressures and temperatures that are difficult, if not impossible, to achieve on Earth. So I'm interested in all of these things, and most of these have played a part in my thesis work so far, but today I'm going to be focusing just on the middle topic, which is using molecules as probes of physical conditions. And where I'm doing this is in the Orion Kl or Orion Kl nebula. So I'm really excited to be working on Orion Kl, in part because it's one of the only things I can find in the sky. So Orion Kl is part of the Great Orion Nebula, which you can see if you're in the Northern Hemisphere, you can see in winter. Even if you're outside of Los Angeles, you're able to see it because it's pretty bright. So it's like the reddish blob below Orion's belt. And in there, you have, somewhere in there, you have these things that are called the fingers or the bullets. So you can see the molecular hydrogen in orange. And it looks like there's an explosion that's happening somewhere in the Great Orion Nebula. And at the center of this is Orion Kl. So Orion Kl had an explosive event take place about 500 years ago. So that's what these fingers are thought to be remnants of, the explosive shocks. Orion Kl is really interesting, not only because it's a violent place, it has lots of exciting chemistry, but because it's nearby. So it's only 388 parsecs away, or at least that's the assumed distance that I'm using in my work. So because it's so close, we're able to study it even at fairly low angular resolution. You can see all the different components in Orion Kl that is much more difficult to do with objects that are further away. So I'm going to be talking about a few of the regions in Orion Kl. So I want to point them out to you to help orient you, especially if you're not familiar with this nebula. So in the reddish pink colors, we have the hot core and source 1. So the hot core is a hot, dense region. It's the traditional site of nitrogen-bearing chemistry. Source I is an embedded star, young star, with a circumstellar disk around it. This is going to be the main area of Orion Kl that I will be talking about today. One area that I won't be talking about too much, but I think is worth mentioning, is the compact ridge. So the compact ridge is kind of like the opposite of the hot core. It's cold, it's less dense, it's the traditional site of oxygen-bearing chemistry. And what has been observed in Orion Kl and other massive protostellar environments is there seems to be some kind of chemical differentiation where nitrogen-bearing chemistry and oxygen-bearing chemistry don't always overlap, and they seem to trace different environments. So we see that in Orion Kl, but I won't be talking about the compact ridge beyond this. The other main region I will be talking about today is this region southwest of the hot core, which I'll refer to as the hot core southwest. It's pretty interesting because it's a hybrid region between the hot core and the compact ridge, or so it seems to be. It seems to be more physically similar to the hot core, but more chemically similar to the compact ridge. And as I'll show later, there seems to be some cool thermal structure going on there. So I think we need to dedicate more time to studying the hot core southwest. Another region is the northwest clump. You also have these low and high velocity outflows throughout the nebula that will shape the physical structure and also the chemistry. And then where the little explosion symbol just popped up, that's about where we think the center of the explosion that took place about 500 years ago is located. So that's just, hopefully that'll give you a bit of an idea of how these different regions are placed next to each other and how they might affect each other. And we know all of this about Orion Kl. We know about its complex structure, both in terms of its physical structure and its chemical structure, because there has been a lot of work done on Orion Kl, both in continuum and line emission and across a wide range of angular resolutions. So my work is a piece of this already ongoing puzzle to understand Orion Kl. I'm looking at Orion Kl using sub-arcsecond resolution, so all less than 1 arcsecond down to 0.2 arcseconds. And this corresponds at the assumed distance of 388 parsecs to spatial scales of less than 350 AU is what we're able to resolve. And I want to emphasize that these provide a different view of Orion Kl from what we've seen in the past. These complement the past observations, and you need to use observations across all different angular resolutions to understand this complex and fascinating place. So to look at Orion Kl, we used 2 compounds. We used the carbon-13 isotopolog of methanol, and we used carbon-13 methanol because it's optically thin. People who do research on complex organic molecules or molecules that have 6 or more atoms know that methanol tends to be optically thick. So carbon-13 solves that issue. It traces the colder and less dense gas, so that allowed us to look at the compact ridge. We also used vibrationally excited methyl cyanide. So this is going to be tracing the warmer and denser gas, and it also gives us an interesting view of Orion Kl because since it is vibrationally excited, this might be because of far infrared pumping by embedded protostars. So it could tell us where there might be some embedded young stellar objects. So what we did with these molecules is we fit the spectrum of these molecules to get parameters, like meaning abundance or column density, temperature, velocity within Orion Kl. So if we take this data cube of Orion Kl and we zoom in on a handful of pixels, what we did is we went pixel by pixel and extracted the spectrum within a single beam from each pixel. And we could get spectra that look something like this. So what this means is that at each pixel, we got a spectrum, and each spectrum gave us a set of parameters. So instead of getting 1 or 2 temperatures toward the hot core, we were able to look at the small scale structure. So using these maps, our goal was to try to understand what's going on in Orion Kl, both in terms of the physical, like the kinematic properties, and the thermal properties, looking at these variations. So I'm going to show you some of the cool things that are in a paper that's currently under review. So first we'll look at velocity structure. And in the past, 3D, looking at the 3D structure of Orion Kl, or Orion in general, has focused on rather large scale. So looking at the fingers or the bullets that I showed earlier, but also just looking at the placement of different components. How are the hot core and the northwest clump oriented, for instance? Here, I was interested in trying to get a sense of how the hot core region, for example, was structured. So we looked at these velocity maps. Note that the systemic velocity is 9 kilometers per second. So in the map on the right, anything that's in red is the systemic velocity of Orion Kl, and then the bluer stuff is blue shifted towards us. So it's moving, relatively speaking, faster towards us. So if you notice, the denser regions, these contours are continuum, or which we think is mostly dust emission. But one thing you'll notice is that these red and orange patches kind of correspond to places where we think that there's a denser material, where there's more dust. And places where there aren't as many contours, where there isn't as much dust, tends to be bluer along the edges and between some of these subregions. So physically, we think what we're observing is gas being blown away by the explosion in Orion Kl, interacting with the dust and the denser gas, and being buffered or slowed as it passes through places like the hot core. So it looks like this, and this will be a little animation. So I went too fast. Let's do it again. But yeah, where it slows down when it's interacting with denser things. Another interesting thing that we see in the velocity map is that there seems to be this elongated velocity structure centered on the hot core. So there was a similar elongated structure found toward IRC7, which is an infrared source elsewhere in the Orion Kl Nebula. And when that elongated structure was detected, it was attributed to a possible outflow. So we're seeing a similar elongated structure here. We also see that this elongated velocity structure is cospatial with broader line widths. I don't have those maps to show you today, but we see broader line widths. So another reason to think maybe we have an outflow here. And then finally, something that's interesting is if you look at the temperature and abundance maps of methyl cyanide, in the center of this outflow region, or what looks like an outflow, you see enhancements in temperature and abundance that might be because of some kind of protostellar source. So that's pretty cool. More work would have to be done to confirm this, but that's what the data show so far. So with that, another thing that we were interested in was thinking about sources of heating within Orion Kl. And that's for anyone who works on Orion Kl, sources of heating are a topic of debate in the nebula. So what we did is we had images both with larger beams and smaller beams for each of our molecular probes. And what we did is we took the difference between those temperatures to be the temperature that we derived in the larger beam, and we subtracted the temperature derived in a smaller beam to try to get a sense of what was going on in terms of thermal structure. So if we have internal heating, we would expect the difference in temperature to be less than 0. In other words, you have a temperature in a smaller beam that is higher than that in the larger beam. Conversely, if you have a source of external heating, you're going to have delta T is greater than 0. So in planar language, the temperature would be higher in a larger beam than it would be in a smaller beam. So I'll show you in a moment what some of these maps look like. But I mentioned that heating in Orion Kl has been a source of debate, and this is especially true around the hot core. One ongoing question is whether the hot cores are internally or externally heated. There's a lot of work that suggests that it's externally heated. The hot core is missing some key hot molecular line emission that you'd expect if it were a true hot core, meaning that there's a baby star in there growing. There are also arguments that it's internally heated, that maybe there is a self-luminous source in there, but it's obscured by an edge on disk. That's another possibility, and there are some others as well. A more recent suggestion that I read that I think is really interesting is that maybe the hot core used to be a true hot core around source 1, and perhaps with the explosion or some other phenomena, that envelope was ejected, and we're seeing what is truly a hot core, but it's detached from the luminous source. So I don't know, it's an ongoing question, and it's always fascinating to see the new ideas about this. So here's my contribution to this ongoing question. So I was really surprised to see this delta T map. I want to note that when you're further away from an emission peak, the certainty of the sign of the delta T is not as great, but we ran some models and show that on an emission peak, like the sign of delta T agrees with whether the model is internally or externally heated. And we see that in the hot core emission peak, we have this very much blue or negative delta T value. So that suggests internal heating. And this is true if we factor in uncertainty. I didn't want to show you a million maps, so I didn't show the uncertainty maps or the maps factoring in uncertainty, but they're all blue. So that suggests that there might be an internal heating source. So from our data, there seems to be a thermal profile and this kind of outflow structure that suggests some kind of internal heating source. Another cool thing about our data is that it gives us a new look at the hot core southwest. So the hot core southwest isn't present in a lot of papers, at least not that I've seen, but it's pretty heterogeneous. So you can see in our maps that that the column density or abundance structure, which is showed on the screen now, isn't uniform throughout the hot core southwest. You have these blobs. You also have these blobs of higher temperature throughout the hot core southwest. So there seems to be some kind of structure, and it looks like these places where you have enhanced abundance correspond to places where you have enhanced temperature. If we look at the delta T map, we also see this. We see that there seems to be some structure. There are some blue blobs, so internal heating, that's co-spatial with the higher abundances and temperatures. So as far as we know, there's no sources of internal heating that have been detected yet, but perhaps there is something going on there. So I'm still trying to think about this and what this means, but ultimately what these maps suggest is that the hot core southwest is really, really cool, and it needs more of our attention. So even if you're not interested in Orion Kl itself, I hope that you can appreciate that the sub-arcsecond imaging that we can do with ALMA allows us to map parameter gradients and learn something or get a different view of different interstellar environments, and that's cool. It also seems that there might be some kind of outflow structure in the hot core, and that our delta T suggests that the hot core might be internally heated. And then the hot core southwest is just really interesting, both physically and thermally. So with that, look out for the paper, hopefully coming soon to AppJ. Thank you very much for your attention, and I will take any questions.
Well, thank you. Thank you very much, Olivia, for the very nice, interesting talk. We have one question from Professor Nesbitt, although he hasn't written, so maybe can we unmute him and he can ask the question?
Yeah, Olivia, thank you. There's clearly an enormous amount of power in these precision, angular and Doppler shifted measurements. this is really going to sound like an ignorant question, because it probably is an ignorant question, but when we look to the night sky and we map it out as a two-dimensional object, of course we're not, we lose that third dimension. How confident can we be, or let me give you an opportunity to explain to me how confident we are that there's not some some overlap, some accidental overlap of objects that are either appreciably closer to us or further away from us, so as to not really be part of a physical object. And I hope that's not an ignorant question. It's just really an honest question that comes up for me.
No, I think that's a great question. And that's something that I also had to think about. Fortunately, less so for Orion Kl, because it has been pretty well studied. But one thing that makes us pretty confident that we're seeing things that are all pretty close together is just that our velocities aren't like completely all over the place. Like you don't have things with local standard of rest velocities of 9 and local standard of rest velocities of like 40 something, for instance.
Right.
So,
Right.
so that's comforting. Another thing is all of the mission that we see overlaps with things that have already been studied. These are all known regions, and people who do much different things than I do have looked at, I don't fully understand it, but proper motions is something that I've seen a lot in the literature, where there's some physics involved with looking at the placement of different objects and the trajectories of things like the fingers and the bullets to create kind of a 3D structure and figure out if these things were closer together at one point, how long would it take for them to be separated apart? To be honest, I don't fully understand it. But there is a lot of work that is done on that.
Olivia, that's great. I'm glad that smart people are thinking about that. That's really good. Since I have you, at Gilla, there, we have people that worry, that stay up at night, worrying about, the time dependence of fundamental constants. Now, your Doppler shifts are always, of course, reference to what your molecules are doing in a cell, just right by you in your laboratory. It's not completely crazy that you might imagine that as you look in some deep part of the night sky, that, that the fine structure constant is changed by, by 1% or something like that. So, I mean, this is a intriguing idea, but would, there might therefore be a shift in frequencies that you would measure and you might misinterpret as a Doppler shift. Is that not a possibility, at least?
Sorry, I'm thinking of a couple of things right now. So I think if I'm understanding your question, the changes in frequencies that would cause changes in Doppler shifts would take probably at least decades to show up in the data. I guess it depends on the object and how far away it is. All of these observations were taken pretty close together. So at least relatively speaking, they're not.
Olivia, when again, this may be like going into details, but I know that people at Caltech, certainly people at Gilla, are really thinking about if H bar really is changing as a function of time, right? Or changing as a function of position in the universe. And so, if H bar, let's just imagine if H bar were to change, that would change the frequencies of all transitions, in molecules. And are you not really using a local reference of what methyl cyanide is you're looking at what frequency an oscillator needs to oscillate at in order to be able to see something, in Pasadena, right, or wherever. And if you compared that to something that's observed in some faraway region where maybe H bar is a part in 10 of the 10 or a part in 10 of the 9 or whatever different, would that not be also show up as maybe looking like a Doppler shift?
Oh, I see. I would think that it would be, I would assume that it would be negligible. Here, I'm going to be honest. This is where I'm going to say I'm a chemist and not a physicist. So hopefully there's a physicist who can answer that question for you. But
Well,
I don't really know too much about.
Okay.
Well, thank you, Olivia. I think we should also move on because we are at 11:27. I don't see any other question at the moment. So thank you very much for a nice talk. We are going to move on to our next speaker. Our next speaker is Professor Christina Puzzarini. Before I introduce Professor Puzzarini, let me just plug our new Twitter account. If you are on Twitter, please follow us. And the new Twitter handle is @ACS Astrochem, @ACS Astrochem. So with that, let me introduce our next speaker. Christina Puzzarini is a full professor of physical chemistry at the University of Bologna, where she leads the rotational and computational spectroscopy lab. After a PhD in theoretical chemistry in 1997, she moved to the millimeter and submillimeter wave spectroscopy lab in 2000. And she also got her MSc degree at the same laboratory. Since 2018, Professor Puzzarini is the director of the Inter-University Center for Astrochemistry STAR at the Scuola Normale Superiore. Her research synergizes experiment and theory with a special focus on astrochemistry, spectroscopic support to astronomical observations, and chemistry of the interstellar medium. Today, Professor Puzzarini is going to talk about theory and experiment for elucidating chemical evolution in space.
So thank you very much for the introduction. Actually, I'm already following you on Twitter. So I just noticed the new account and immediately decided to follow. Let me share the screen. Okay, so today's challenge concern the chemical evolution in space, and I will focus on the sensors of the detected molecules and the formation of these detected molecules. Or better, I will focus on the contribution we are trying to give to the field. In this slide, we see a schematic representation of how to go from a molecular cloud and go back to the molecular cloud with a complete chemical characterization. So you see the starting point is the detection of the molecule in our environment, and this is the result of synergies between the laboratory spectroscopy and radio astronomy. From this detection, we derive the molecular abundance, even if sometimes things are a little bit more complicated, so we need also to compute or derive collisional coefficients. Then we have the reactivity, which allow to explain how the molecule detecting the react and how they were formed. If we can collect, and this is really a huge effort, all the information on the species that are present, then we can complete the chemical network and have a reliable and accurate chemical model. And then we, at the end, have a complete chemical characterization of our molecular cloud. But of course, this is really a huge effort, so we are very far from this puzzle, but we try to in my laboratory to provide some information for what concern laboratory spectroscopy and reactivity. The strategy we use rely on the interplay, whenever possible, the interplay of the experiment and theory. And I will show you some example to see how our strategy works. Let's start from the detection of new molecule in space. So this is something that we all know nowadays, especially thanks to the huge number of detection by Pepe this year. The chances of the molecule is around 250. And they are, as you well know, well documented in the Cologne database. And also we know that most of this molecule, 80% probably, something like this, have been detected thanks their rotational fingerprints, so their rotational transition. So they were detected thanks to what I mentioned before, this synergy between the rotational laboratory spectroscopy and radioastronomy. But there is something more in this laboratory, because there is a strong interplay between experiment and theory. So I would like to give you just an idea of what's the strategy. First of all, we start from the quantum chemical calculation of the spectroscopic parameter we need for predicting the spectrum. So we have the usual Hamiltonian with they give us the list of parameters we need. Usually the rotational constant are the most important, then we have centrifugal terms, and sometimes even in even for astrophysical purpose, we need hyperfine parameter. And here you can find some literature about the work and the state of the art in this field. Then we move to the recording of the spectrum. In Bologna, we have it's something strange because we are moving, so the two spectrometers will become just one with more cells. So we have a millimeter per millimeter wave spectrometer, a frequency modulated one. So we have phase locked radiation, second detection technique. So we record the second harmonic of the actual rotational spectrum. I decided to show you some example for what concern prebiotic molecule, because actually we are really working hard on this type of molecule in the last years. In particular, we are very fond of imine. You see the imines are anyway let's say, more detected than the amine, but definitely less detected than the corresponding dehydrogenated species. We focused on the investigation of the imine because we have a powerful way to produce them inside the cell via the flash vacuum pyrolysis. And you see now the scheme of our spectrometer, and maybe you have noticed that something is different in this picture with respect to the one I showed you previously, and is this oven. At the beginning, we had a pyrolysis oven outside the cell. Nowadays, we have a dedicated cell, a quartz tube surrounded by this oven, and in this way we can have a better production, in the sense that we can directly, immediately probe the species produced inside, directly inside the cell. And I would like to show you a very, very brand new example, aluminum, very brand new because the manuscript is still in preparation. So the schedule is typical of our work. So first of all, we compute all as much as possible. I mean, from an accuracy point of view, we compute all the spectroscopic parameter. In this case, in this specific case, we there was some knowledge about the rotational constant, but still we needed information, accurate information on the dipole moment component, the energetics, centrifugal distortion constant, nuclear quadrupole coupling constant. Then we recorded and analyzed 1 to 3 millimeter wave spectrum to prepare a line list and proceed to the search in the in a specific nebula. Here, an example, just for those that are not confident with rotational spectroscopy, to show you how complicated the spectra can be. We detected the trans species, but not the cis one, which are the less stable. And we successfully observed both the syn and anti-trans aluminum. And then we moved to a tentative detection. Actually, we pass our information to Victor, and we have a tentative detection in the sense that we have 5-6 transition above the noise level. The second example is it's from the last year, so it's not so brand new, but I think it's rather interesting because it's from the rotational spectroscopy and quantum chemical computational point of view. This species is rather large. The idea to investigate this molecule came after the detection of benzonitrile. So I thought, well, if benzonitrile is there, maybe also the hydrogenated species is there. Nothing was known, so we started, in this case, the investigation from scratch. So we put the largest effort in the structural determination, because you surely know that the equilibrium structure of the molecule straightforwardly provides the equilibrium rotational constants. We corrected to move from the equilibrium to the vibrational ground state. We computed all the other parameters like quartic centrifugal distortion constant and nitrogen quadruple coupling constant. We characterized the energetics, and we ended up with an accurate prediction of the rotational spectra. And you have here an idea. So this is the E isomer. This is black line is the recorded transition. In red, we have the prediction due to dipole hybrid functional, similar. So let's say same quality of this level of theory. In blue, we have something really interesting because it's something we are working on. It's a sort of a Lego approach. So we take the piece of forming this formula from the structure accurate experimentally known from other molecules, we put it together. So you see the prediction is not so bad, and the effort, the computational effort, is really low. And this is in green, the result of this level of theory. So you can see the accuracy we can reach with our calculation. And you have here the comparison between the experiment and theory, and you see the average deviation is 0.15%. So a really good agreement. In this case, it helped a lot the fact that we could, thanks to the collaboration with the Jens Uwe Grabov, we could record the spectrum and sign the spectrum in the centimeter wave before moving to the millimeter wave region. We asked to Brett, actually the PI of this project, asked to Brett Neguai, but no detection so far. Probably the dipole moment is not enough large. I hope that I gave you an idea of our strategy and what we can get with our strategy. And so for what concerns the work in the spectroscopy lab. Now I would like to move to the second topic, so the formation of molecule. Well, in this case, theory dominates, and we have just a flavor of experiment. So how we proceed? Well, we all know that molecules are formed in the gas phase, or either in the gas phase or on the surface of the interstellar dust. So you have to choose which type of reactivity you would like to pursue. Well, I'm a rotational spectroscopy since 1993 when I got my undergraduate degree, and so I'm a gas phase woman. So I choose gas phase. In any case, you have then to choose the suitable precursors. Then you have to investigate all possible reaction mechanisms, select those that they are interesting to build the accurate thermochemistry, and the last step is kinetics. Once again, the example will be in the category of prebiotic molecule. The first example was inspired by this paper. When I saw this paper, I said, wow, this is really what I would like to get from computation lab detection. So the perfect paper. And when I saw the molecule, I think I have an idea how this molecule can be formed. And there were some idea in the paper, but none of them really convinced me. As I told you, you have to choose the precursor. Of course, in this case, the precursors should be more abundant than your final product. And of course, they should be present in the same environment. And there was already some a selection of potential precursor, and but there was one missing, and I was interested in. Likely methanamine is rather present present in different environments, and so I went for methanamine and the C2H radical. So the choice of the precursor was done. Then we moved to sampling the reactive potential energy surface. For doing this, we rely on a really low level of theory, something like a global hybrid density functional in conjunction with a triple database set for those that are confident with computational chemistry. But we use B3LYP, which is really nice because I mean, it's fast. It allows you to get a lot of results really quickly. But it often happens that any a stationary state that is a minimum of the B3LYP level, then it is a transition state or nothing at a higher level of theory. So before proceeding, we need to investigate at a higher level of theory, the paths that are interesting. And then we need to improve the further energetics to get the best possible. And this is the result. So what we get. So you see, we all this path are open because we have to keep in mind. Olivia already pointed out the interstellar medium condition are extreme, so the temperature is very low, the density is extremely low. Temperature very low means that the reactants have their own energy. They cannot count for external thermic energy. And so all the barrier should be submerged in order to be overcome. In this case, we have three possible attacks. So our radical can attack the end of methanamine, the C end, and even the pi system. But the pi system then move. So let's see, relax to the other two passes. And then once we have a clear mechanism in our hand with a high level thermochemistry, then we move to the kinetics. And you see there is a rather roughly a 2:1 ratio for the E beta rate coefficients. Something that I would like to stress is it's really so important to push theory so much in the evaluation of the energetics. So my answer is, of course, yes. And I will show you some example to stress this. This is a work done some years ago. And it's the formation path, gas phase formation of formamide. And in a previous work, this CBS QB3 was used, improving the level of theory, ended up in a difference of 2 orders of magnitude in the rate constant. This is also the reason why this other example is meant to stress the reason why we always push so much the theory level in the energetic evaluation. This is the reaction between methylamine and the CN radical. We investigated this reaction because we hoped to produce amino acetonitrile. You see, it's produced all the barriers, so the path is open, but there are 2 most stable products. So it is not such an interesting reaction mechanism to form amino acetonitrile. But this picture is not complete. Actually, the complete picture is this one. But you see the TS, transition state 4 and transition state 5, are emergent, so they lie at higher in energy with respect to the reactants, and so these paths are closed. And this means that the most exothermic reaction cannot occur. And you see here, the expert understand what all this term means. So really, it's hard, really very hard to go even further with respect to this level of theory. And actually, such investigation in this level is important because this reaction was experimentally investigated using the CRISO technique. And unfortunately, low-level calculation guided the experiment, and they ended up to the wrong conclusion that channelite is produced can be produced by this reaction, while we see the channel is closed. And then I mentioned the flavor of experiment. So the question is, what we can do with the rotational spectroscopy in this field? So can rotational spectroscopy help us in studying reactivity? So we can find a synergism between experiment and theory also in the fields of reactivity. So, well, not directly, but indirectly, yes. Because if this reaction mechanism and so this thermochemistry and kinetics is correct, then the reaction should produce this radical CH3NH and this other radical CH2NH2. And for this reason, in this work, we also investigated in detail these radicals. The structure, which means the equilibrium rotational constant, was determined at the highest possible level. For experts, they can understand how high is this level. We computed accurately at the highest possible level all the spectroscopic parameter, also all the hyperfine parameter, and we provide a prediction. Actually, one of these radical, I think is Susanna. Yes, I think it's Susanna and Vinicius Weber. I followed a seminar gave by her, and I think one of these two radicals, she was trying to investigate experimentally one of these two radicals. So I said, please check this paper, because you have all the spectroscopic parameter computed. I have to say that we haven't think about the spectroscopy for the moment of this molecule. But if we go back to formamide, well, this is the complete path, a very complicated path, published 5 years ago. And the interesting outcome is that in addition to formamide, also the E and the methylaminic acid are produced. For this reason, we accurately characterize this species from a spectroscopic point of view. And we are thinking how to produce them. Actually, using the pyrolysis, flash pyrolysis system, flash vacuum pyrolysis system I showed you before, we think that with not too much high temperature, but with a reasonable temperature, maybe we can starting from formamide, we can see the isomerization. Let's see if this work. I would like to conclude with a question. So we investigated
Professor Puzzarini, we're coming to the top of the hour. Can we close soon?
Yeah.
Okay, thanks.
I'm going to conclude. So when we investigated this path, the reaction between C2H and methenamine, we realized that the path was very similar to the reaction already investigated between methenamine and the CN radical. And so it was proposed that this can be a general mechanism for the formation of complex imine. And since the products of the reaction of CN with methenamine have been detected, and the products of the C2H with the methenamine were detected as well, my PhD student, Silvia Alessandrini, thought, well, maybe the CP radical perform like the CN. And indeed, you see the reaction paths is really similar. And so she also accurately characterized from a spectroscopic point of view, computationally, the potential product, the product of this reaction. I can skip this. This is another interesting example. To in this case, we push even to pentacle, and it's the demonstration that you can treat from a computational point of view intermediate structure that have a multi-reference character, even this high level. And the phosphorus, this is the kinetics for the N plus OH reaction, and it's completely different from what you get for the phosphorus plus OH. So I have to thank a lot of people for being able to show you so many results. First of all, my group, a very young group, because Silvia, Francesca, Nijing, and Alessio are PhD student. Mattia is a young postdoc. Luca, the two Lucas are well known in the field. I also would like to thank the collaborator of the studies I showed you, and thank you for your attention.
Thank you, Professor Puzzarini, for the nice talk. I mean, we have at least one question, so we'll go through that. Thank you for this talk. This is from Leah Dodson. Interesting question here. What does CBS QB3 miss compared to CCSD parenthesis T for them to result in a 2 orders of magnitude difference?
Oh, this CBS QB3 method is like the ones we use. It's a composite scheme. The problem is it's rely on very low quality structure, and also has some empirical parameter. And the test cases we did show that it tend to underestimate the reaction barrier by a few to more than a few kilojoule per mole.
Okay. Well, I don't see any more questions. We are a bit over time at this point. So I would like to thank both our speakers today. And so thank you very much for your talks. And thank you all who have joined. Please join us again next month. Month of October, we will have 2 speakers again. And we will announce the speakers soon. So thank you again, and have a great day. Bye.
Thank you. Bye.
Thank you.